Alright guys, let's go through the answers real quick, everyone. If you look at this question here, figure 9, blah, blah, basically there's 3 resistors here, right? Wait, where did I go? If you look at this here, there's 3 resistors here, right? And first and foremost, they ask you the current and X and Y, right? So from here, guys, the key thing to these kind of questions is you must remember that the current flows like water, guys. Meaning to say, if it flows starting from here, right? What's going to happen is the current is going to split here, and then continue flowing here, and then split here, and then split here, and then continue flowing here, guys. You must always remember current flows like water. Besides the twins and Charles, who else is missing? How come I feel like someone else is missing? Okay, anyways, from here, because you already identified that here is 7.7 amperes flowing, right? 4.6 flows down here. Means to say whatever that's remaining is going to be 3.1 here amperes flowing, right? It's going to be 3.1. And then this 3.1 flow is going to flow here as well, and it's going to remain with 0.8 amperes here. That's why it's going to be 3.1 and 0.8 amperes here. All right. Did most of you guys get it correct? Excellent. Good job. Okay. Then after that, they talk about the resistance in appliance T, right? Which, if you're asked to find resistance, you must be given at least 2 things, right? What 2 things must I be given? Volts and current. Very good. Because if I use the V equals to IR formula, I'll understand that R will equals to V over I, right? Which in this case here will be 110 divided by 0.8, and if you press in the calculator, you're going to get quite a big number. How much is the number? 1375. You get the raw number of 137.5, right? But do I write 137.5 here on the dotted line? No. How many maximum? Maximum 3 significant figures, which is 138 ohms, guys. What happened here? Oh, okay. Let's check answers. From here, they ask you to calculate the combined resistance of R and S already, which you realize is in parallel, right? So it's very straightforward. Parallel is just, what's the formula again? 1 over R plus 1 over R, which is 48. Right, which you'll get 3 over 48, right? But this is not the final answer, right? Because this thing here is 1 over RT, guys. Remember, I emphasize this because I see a lot of students, as soon as they finish doing this, they give me this as the answer. Come on. Wait, remember, this is not the final answer. You need to flip it one more time to get the RT. So in this case, it'll be 48 divided by 3, which will be obviously 16 ohms. Okay, very straightforward. And from here, they ask you to find the power developed in appliance R. Right, power is either going to be energy over time, or it's going to be VI, right? Which obviously is this case here, right? V and I of R is how much? V is still 110, right? I is 4.6, right? So power will be equals to 110 times 4.6, which will give you 506 watts. Okay. Okay, good. Then after that, energy converted in 2 minutes. Energy is equals to VIT. Most of these questions are just applying the formula. The trick is not remembering the formula, guys. The trick is to know which one has what information, like how much voltage is there, how much current is there, and how much time is there. In this scenario, it will be 110 multiplied by the total current of 7.7 multiplied by the time of 120. And if you press that in your calculator, it will be a very big number. How much is a big number? What? 1064. Standard form. Did everyone get the same answer, guys? Did anyone else get different, or anyone wants me to explain any part from here or not? Sorry, what? Oh, good. That was a test. Ah, 200 bucks. Okay. Okay, everyone. Remember, guys, it's always good practice to have a big number converted into standard form on the dotted line, because most of the time the mark scheme, if it's a big number, will be in standard form. And when I say a big number, it's any number that's more than 4 units, 4 digits. Okay, then from here, I think all these are quite straightforward. I'm going to go through it very fast because I want to cover. Hey, by the way, did Gilbert announce it yet? We're going to have a revision class for your test. You all know, right, on the 22nd. Did Gilbert say 22nd? Which is 1 week before your. Everyone pay attention. 22nd on Sunday. Amen. Right. We are going to have an extra class to revise before your exam, because you guys have the exam start at the end of October, right? End of October, right? So we're going to do it on the 22nd. Okay. On the 22nd, what I'm going to do for my class, for the physics revision class, is I'm going to revise basically everything. I will try to cover up all the important parts from the start all the way until electricity. But I just want to know, right, for your tests, will they cover the AC and DC generators? Have you guys even started that in school already? Do you guys have the exam? You started already in school, AC, DC? Wait. Ah, 不是，它是那个 generator 和 motor 你们做了吗？哦，还没有啊。So I need to know where your scope is until, because depending on where your scope is until, right, today I'm going to decide to proceed or not proceed. Basically, I just need to know, will you guys have dangers of electricity in your exam, which is what I plan to cover today? Will you guys have magnetic induction, electromagnetic induction in your scope? Does anyone know? Huh?
I've not heard of any so far. I think only to feel like
no magnets, confirm. If it's no magnets, then today I'm going to start doing the revision already. We're going to do past year papers already today to cover back everything from the start all the way until here. Confirm, no magnets. What about dangers of electricity, got? But that one is quite a short chapter. We can go through that today in probably half an hour.
like what?
No. Okay. Let me show you the scope. So basically, the first part here was we learned about magnets. All this I think this one maybe will come up. Right, but when I talk about electromagnetic induction, is basically generating electricity with the help of magnetism already. All these here, like this one here, then Lenz's law, which I assume you guys haven't learned. Then, yes, the Fleming's left hand rule and right hand rule. Then you're going to learn about these generators and motors. This is a generator, and this one is a motor. This one is a motor, which a lot of students don't like this chapter. Everyone hates this chapter. But it's actually very easy, don't worry. I have a perfect way to simplify the understanding. So don't worry about that. But I just need to know, this one confirm not out. Then the next 2 days exam. So should I cover this or not? Confirm, It should be the same, right? Everyone should be in the same exam scope, right? I mean, I know there's different teachers, right? But no way she don't cover and then you guys cover, right? I think I don't know. Okay, anyways. But dangers of electricity got I think. If it's just electricity, it may be. Anyways, we cover it today. It's a very short one. Okay, anyways, hey, I'm going to go through all these answers quite fast because I think some of these questions are quite easy. You should be able to do it. Close this one. Oh, you need to perfectly align. Okay, anyways, let's go through these answers real quick, guys. So first and foremost, they give you the information is that an ammeter is 3 amperes, right? And if I look at it and they are the same identical lamps, means to say they have identical resistance, then how much current should be flowing on each? 1.5, quite straightforward, right? 1.5 amperes here. Then after that, if a voltmeter is connected to lamp key, what will they read? They already say that this is 6 volts, right? Then if I have a voltmeter here, how much will it be? 3. Wait, parallel, parallel is the same voltage. Current is the one that splits. Remember, guys, in series, current is the same, voltage splits. In parallel, current splits, voltage is the same, guys. And this is a very important foundation understanding, guys. It's like all these lamps here, right? You see all these lamps here, right? Assuming that they are the same lamps, they'll get the same brightness because all of them receive the same amount of voltage from the grid itself, guys. Right? Because all of these things are connected in parallel. You need to know that all of everything that is connected in parallel should have the same voltage, which in this case here will be 6 volts. This guy will get 6 volts and this guy will also get 6 volts. Alright? Okay, 6 volts. And calculate the resistance. Quite straightforward. It's going to be 4 ohms using the Ohm's law. If you did not get the same answer, please say something. I'm assuming most of you guys can do this already, but if you did not, please make sure you say something so that I can explain to you until you understand. This is a very important chapter, guys. You want to ask me something? Oh, okay. Okay, I'm going to move on. And then this one here, what's the total resistance? 15 ohm, quite straightforward. Calculate the current which flows through is going to be 0.2 amperes. Right. Okay, next page. Then after that, this is a trick question. Sorry, this is a concept question, guys. Let me teach you how to do it real fast. In these kind of questions, right, you can do it either 2 ways. First and foremost, you identify that 0.6 amperes flow here, right? 0.6 amperes flow, you could either use Ohm's law, right, to find that the voltage is going to be 6 volts here, 6 volts here, and 6 volts here to find the current here. Or if you really look at this, right, this is double the resistance, right? If you double the resistance, how will the current change? It will half, guys. And I know for a fact that it will be 0.3 amperes. But if you're not certain, you're not 100% sure, you can always use the Ohm's law formula as your basic guideline to check whether your answer is correct or not, which in this case will obviously be correct. Okay, and 0.3 amperes here. Calculate the current flowing in the battery. How much? How much should the battery have? Good. Someone answer me here. If I know here is 0.6 and here is 0.3, how much will the battery have? Yeah, 0.9. Why are you guys hesitating? No. Yes, but I hope. Okay, then the voltage supply is obviously going to be 6 volts. Okay, I think most of you guys did this question correct also. But if you're wrong, make sure you let me know. No, I'm not going to beat your ass, bro. This is something that's new. It's not like we repeated it multiple times. 会开心，我一直看你有叉，你做错是哪这个？有。If you don't understand, you must ask 这个 chapter 很重要Okay. All right, and then this one here, I want to highlight this, which a lot of students, some of you guys may have done this. If I want to find the total resistance here, what do I do? Do I do like 1/10 plus 1/10 plus 1/10 here? If I want to find the total resistance, should I? How many of you guys say yes? If I want to find the total resistance of these 3 things, should I go 1/10, 1/10, 1/10? Why not? Very good, because only these 2 are in parallel. These 2 in parallel are in series with this one here. Right, so what we usually do is we combine these 2 in parallel first, which is obviously going to be 5 ohms. I think most of you guys got it also, right? And the total resistance is only going to be 15 ohms because this 5 ohms combined will be in series with this 10 ohm. Did anyone not get that? This is very important. Comes up quite often also on your exam. You need to know which one are in parallel, which one are in series. Okay, good, excellent. Then after that, they ask you to calculate the current in each resistor, which you first find the total current here. How much is the total current in the battery? 0.4 amps, right? So here will be 0.2, this will be 0.2, and obviously this will be 0.4. These two on top will be 0.2 each, and the one at the bottom will be 0.4. Okay, 你做对了，全部都对。Okay? Alright? How come you didn't do this one? But you understand what I'm talking about, right? You first find the total current from the battery first. Then you imagine how it flows up. Right, which will obviously split 0.2, 0.2, then combine back here to be 0.4. Okay. Six on? Oh, because they are in parallel. You could use the current and resistance here to find 6 volts, or you could use the resistance and current here to find the 6 volts. Okay, the drawing looks a bit 捋水 lah, right? But you identify here is 0.6 ampere, right? And here is 0.3 ampere, right? So if I find the voltage here, this is 6 volts, right? Wait, you can't more. So there's a 6 volts, then here for sure is 6 volts, because they're all in parallel. Okay, good. Clarify your doubts. Make sure you clarify, guys. It's very important. Okay, everyone? Yes, can I help you? Which question? This one? The 6 volts one? Okay, so from the question, you know that this is 0.6 ampere already, right? Oh, you mean this one? Oh shit, you mean this one? Okay, which question? C, is it C? So you're asked to find the current in each resistor, right? So in order to find the current in each resistor, I need to know these 3 things, right? But I don't even know how much is the current being supplied to the circuit first. So I know that the total resistance is 15 ohm, right? And I can find the total current because I have the total voltage of 6 volts, So using the Ohm's law, V equals to IR, I would have been equals to V over R, right? Which would give me 0.4 amperes, right? So this 0.4 amperes flows here first, right? And then when it comes to this intersection, same resistance, means to say it will split equally, right? Then it will be 0.2 and 0.2 here, right? This 0.2 will flow all the way until this intersection point where they combine back, right? And then combine back here will be 0.4 also. You get what I mean? So it's 0.2, 0.2, and 0.4 amperes. Make sure you write your units. Good, clarify your doubts. Okay, I move on. Okay,
And not to stretch.
Series, no question here. 17 ohm. Parallel 1 over 2 plus 1 over 5 plus 1 over 10. Hey, why do I keep seeing students smash their calculator like that? Yeah, then he's smashing it with. That's exactly what my other student told me. Okay, anyways, press in the calculator, find this and flip it. How much is this one? 1.25 ohms. Okay, okay, I think everyone got it. Okay, and this one here, what's the answer? Rio, what should I write here? Which one will have the larger current and why? Parallel or series will have the larger current. Huh? Equal? For sure parallel. Why? Yo, hey everyone, listen up. Imagine, right, all these lamps here, right, they're connected in series. Do you know how high will the electricity bill be? Assuming lah, 1 lamp is 1 ohm lah. Okay, let's make it another way around. 1 lamp is like 3 ohms lah, right? 3, right? This is easily at least going to be like how many 3 did I say? 4, 8, 10. That's easily 30 ohms, right? If it was 3 ohms, but if I connect them all in parallel, it will be 1 over 3 plus 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 1 over 3. And then later on, I need to flip it lagi. Right. So imagine if I connect them all in parallel, right? The resistance for sure will be lower, right? And if the resistance is lower, according to my Ohm's law formula once again, a lower resistance will have how much current? Higher current lah. Right. So this is the reasoning. You connect everything in parallel. Number one, all of them will have lower resistance generally, and all of them will have the same amount of voltage when you connect them in parallel. Have that in your mind, guys. This question comes up quite often. You need to know that parallel circuits generally have lower resistance and thus have a higher current flowing through it. Okay, so your answer should be parallel. Why? Has a lower resistance in the circuit, according to Ohm's law. Okay, moving on to the next part. This question I want to highlight a little bit because this one here is a relatively hard question compared to all the questions that we've done so far. So if you look at this question here, they say that they have 3 ohm, 6 ohm, 6 ohm, and 12 ohm, right? So 3 ohm, 6 ohm, 6 ohm, and 12 ohm, and it's connected by 12 volts here, right? First and foremost, it asks you to calculate the total resistance when both switches are closed. Both switches are closed means to say this is connected and this is connected. Do I do 1 over 12 plus 1 over 6 plus 1 over 3 plus 1 over 6? No. I'm first going to combine these two parallel ones first, which is 1 over 12 plus 1 over 6, right? Which will give me 4 ohms, right? After I flip it, right? Right. So this here is only going to be 4 ohms. And then I do the 1 over 3 plus 1 over 6, which in this case here will give me 2 ohms, right? Right. So this one here, this 4 ohms, hey, pay attention here where everyone, especially those that didn't do it. This 4 ohms is actually in series with this 2 ohms. So the total resistance here is only going to be 6 ohms. Okay. Did you skip the whole question because you didn't do the first one? Or you couldn't do the first one? I said, hey, what? You flipped to this page and you just what? Okay. Okay, guys. So this is how you get 6 ohms. You are not supposed to 1 over everything. If it's 1 over everything, then they'll all be in blocks, like resistance. Yes, okay. Anyone's got any questions for this part here? Okay, good, excellent. Next, they ask you to calculate the total current when both switches are closed. Current, very straightforward law, is just like 12 divided by 12 divided by 6, right? Which is going to be 2 amperes. Okay? Because it's just using the Ohm's law once again. I don't want to do the calculation, I'll do it yourself. Okay. Then after that, oh, by the way, how many of you guys found 6 ohms for this question here? Can I have a raise of hands? Okay, good job. Okay. Gigi, what do you do for this one? How come, what do you do a different? You did the 1 over everything. Yeah, okay, if it's 1 over everything, it will be like block onto block onto block onto block. Then you can do the 1 over everything. Okay, Okay, then after that, I ask you to calculate the current in the 3 ohm resistor when switch S is closed and switch 2 is open. Right now, it's a totally different scenario. Switch S is closed and switch 2 is open. Guys, in terms of the current flow, right now, if this is open, right, the current is going to flow like this, right? Flow here, flow here, flow here. Wait, pay attention. Flow here, flow here, flow here, gonna split, and then flow here, right? So it means to say, is this thing still, do I still need to take this into consideration? This thing is like effectively not there anymore because no current is flowing through it, right? So just now we found that this is 4 ohms, right? Right now, how much is the total resistance? It's 7 ohms. If switch S2 is open, once again showing you that if you connect everything in parallel, it actually has a lower resistance because just now if everything was connected, it's 6 ohms, right? Right now with one thing not connected, it's 7 ohms. It means to say it's increased now. Right, so you're supposed to find the current, right? Straightforward, 12 divided by 7. Ohm's law once again, V over R. Right, we should get a very big number. What's the number? 1.7? 1 ampere. Okay. You got it right? Good, excellent. Okay, then after that, switch when find the current when both switch are open. Both switch are open. Usually the current is going to flow like this, right? Right now, how much is the total resistance? It's 9 ohms. Right, when both switch are open, the total resistance is 9 ohms. You gotta find the current is very straightforward, right? Once again, it's 9 divided by 12, which once again is a very weird number, 1.33. 1.33 amperes. Okay, everybody. Anyone has any questions with this so far? Sorry? C, yeah. Calculate the current in the 3 ohm resistor. Okay, so right now the scenario is this switch is closed and this is open, right? So according to the flow of current, it's going to flow like this here, and then split here, right? And flow here, means to say effectively this resistance is in play and this resistance are in play, right? Just now we already found that here is a total of 4 ohms, so I don't redo the calculation. Means to say the total resistance in this circuit is only 7 ohms. Right, so if I want to find the current in here, I'll find the current here. It's basically the current here because it didn't even split, right? Right, so in other words, I need to find the total current. So it's 12 divided by 7, which you'll get 1.71 amperes. Very one. If you can master this series and parallel circuits, I would quite confidently say that your electricity chapter until the generator and the motor should be quite easy, right? But if you are struggling here, you're going to have some trouble later on as well. Hi, everyone. Okay. Okay, let's move on to the next chapter, which is a very, very short chapter. I just want to cover it in case it comes out in your exam, guys. If you look at the hazards of electricity, right? If you look at this chapter here, we're talking about the hazards of electricity, which is literally common sense stuff, guys. I don't think I need to be the first one to tell you all these dangerous stuff, but it's in your syllabus, so it's good to at least read through what I have here. It's nothing much to explain. Everything is self-explanatory on its own. Just read through the damn thing. Okay, I already taken the time to compile all the useful information already. Okay, hazards of electricity include the damaged insulation. Like for example, all these wires inside is the copper that conducts electricity, right? This white color part here, this is the insulation. Usually, especially the iPhone cables, I realize if you keep folding and folding and folding and folding, eventually the rubber wears out and then it exposes the copper inside, which could potentially electrocute you. But if you have like a relatively more high voltage, right? Usually on top of the insulation on the outside, they'll have another layer of insulation inside one, which is supposed to separate the earth, the light, and the neutral wire. Okay, so damage to insulation is obviously going to give you some trouble. As you can see here, insulation of wire protects us from touching it. Exposure to damaged insulation may lead to electrical shock, and obviously damage to live wire and neutral wire may lead to short circuit. This one here is quite interesting because it's Cantonese saying that we have all when we were young, we always used to say this. You know, have you guys ever heard of the word chi ma kan before? Anyone here speaks Cantonese? Okay, it's not relatable, then forget it. But anyways, in terms of electricity, okay, I must mention this. You know, chi ma, you know, like our brain sends nerves, sends signal through the nerve to all our body, right? For example, if I want to move my finger here, my brain is probably sending nerve signals to my hand and then controlling the fingers. But you know, the word chi ma kan literally means to say, right, the nerves are connected. So for example, if I want to touch, I want to use my hands here, right? Maybe I'll accidentally move this here, right? Because the nerves are sending wrong signals to different parts already, you know. And this is really applicable in real life also. Inside these wires here, there are three main forms of wires: live wire, neutral wire, and earth wire. If the damaged insulation, right, the insulation is damaged, right, what's going to happen is, right, the live wire could touch the neutral wire, which could cause a short circuit. You know, when I was in university, right, I literally had one of these things, which had a short circuit, which had a live wire touching the neutral wire. You know what happened? Every time I plug in something here, right, and I switch this on, the whole thing, poof, my whole house trips, you know, because the live wire is shorting everything, right? And then when I first saw this, I'm like, holy shit. Is this thing fucked, or is it my house fucked? And I just think about it. I think it's this thing, right? And I tried, you know what I did? I kept it all the way until the last day of school. You know what I did on the last day of school? I took this, I plugged it into each of the faculty.
No.
Starting from the engineering faculty. Tack, poof, the whole building goes off. I'm like, oh my god, it actually worked. Plug it out, stuck it into the teacher's lounge. Tack, the whole building goes off. Then I went to the exam hall. I had a look inside. They're having exam. You know, in university, there's like layers and layers. 100 old people taking exam together, you know. Wow, then look at the time. You know, like on the whiteboard, they'll have like a timer to say how much time you have left on, right? Wow, let's extend their time. Plug it in, tack, poof, the whole place went off, you know. I'm like, oh my god, man. I threw it away after that. It was in my uni days. That was like almost 8 years ago. Wow. I got away. I tell you, I went to every faculty at the school, the engineering faculty, the business faculty, the teacher's lounge, the exam hall, the auditorium. Wow, the whole school went black that day. So with great power comes great responsibility, and of course with great knowledge, you can do a lot of nonsense with it on the last day of school. Yes. It was a fun time, man. And then you can see after that, right? You can see like all the guards walking around, but what's happening? Part by part starts to go black out. Wow, it was fun, man. Anyway, yeah, I think it was like a one in 1,000 chance of that happening, man. Because obviously I was poor back then in uni, right? Then no money, then got to buy all the cheap extension cables, then one of it is like GG'd out already. And I'm like, oh my god. You could, but be very, very careful, because if it's not good, if the chances are, it's quite slim, but if you did it wrong, right, the thing could explode. So don't try it at home, boys and girls. 15, I think below 20 bucks, 10 bucks, I don't think you can get it. Below 20 bucks. Yeah, I'll teach you how to do it later. The theory, but I must say, don't do it at home, guys. There is obviously a danger to it. Okay, and then obviously overheating of cable is one of the problems as well. Overheating of cable usually is due to the either too large current or the cables are too small, right? If you remember what we talked about in terms of resistance of a wire, which is dependent on the length and the area. If your cross-section area of the wire is too small and too large of a current flows through it, obviously it's going to generate heat. And then if your length of the cable is too long, obviously that's going to generate heat as well, right? Which you can see here. Causing fire is like 1 in a million chance. I haven't seen it yet. But there's still a possibility. Okay, damp conditions obviously is one of the problems as well. If you come up from the shower and your fingers are wet and then your switch is a bit fucked up already, then you click onto it, that could be a problem. of electrocution. But that's also 1 in a million chance, because right now, as I understand, the switches are very well insulated, and they, even if your fingers are wet and usually no problem, to my understanding. But of course, you're more than welcome to try. Fingers wet. Got you, idiots. Okay, and then this one is my favorite of them all, guys. The excess current from overloads of plug. As you can see, usually these kind of scenarios are most commonly seen in the Asian household, right? So for example, you buy a tree extension plug, then suddenly, there's a 4th electrical appliance on. Buy another extension to another extension, right? Then after the extension and the extension and extension and the extension again. Huh? What? Oh. Yeah, so this is the most common Asian thing that you see. Me myself, I also like to do this because sometimes like not enough extension, not enough what's it called plug heads, right? Then obviously that's going to be a problem. But it's actually not advised to. Especially usually if let's say you use very small electrical devices like your phone charger, your lamp, or whatever, all the small electrical device, right? You can keep extending, no problem. But if you use like relatively higher electrical voltage, like for example, your fridge, your TV, your, I don't know, something that requires quite a high amount of voltage. Laptop is still okay. You extend, right? This thing is not made to extend that many times. So if it's especially a large voltage, then that's going to be a big problem. So don't do that. I will at least be smart about it. Okay, so there's nothing much to explain here. Please read through. You need to use this as reference, this page as reference. There's literally nothing much to explain here. I just go with it, okay? Now this one is important though. The live wire, neutral wire, and earth wire. If you notice, all our 3-pin plugs here, right? All our 3-pin plugs here usually have 3 points, right? These 3 points are not just for fun and to ease your way to plug it into the three holes there. Each of these things here have a different purpose. This is usually the earth wire. If you remember from 4.2, earth wire is for you to discharge excessive amount of electrons back into the ground. Right, remember the earth wire we talked about from 4.2? Right, this is that. Usually this thing here will be connected to a metal part from this thing, which will be connected to another metal part of the electrical device. For example, maybe this thing here definitely has a 3-pin plug also, right? The earth wire will be connected to some metal part of it, so that if there's excessive amounts of electrons, it will just transfer all the way to here and then go back into the ground. No problem. Then there will be a live wire here. Oh shit, the live wire is this one. This live wire, you can assume, is the positive side of the electrical circuit. The current goes in here, and the neutral wire, the current goes up here. Okay, so simplified, earth wire, excessive amount of electrons, live wire, current goes in, neutral wire, current goes out. Okay, so on top of these 3 things, right, you'll notice that if you ever open it up before, you'll see something like this here. This is something we call a fuse, guys. Have you guys ever opened this before? A 3-pin plug? Yeah. If you open it up, you'll see something like this. It will look something like this, a real thing. It looks something like this. This fuse here, is basically like a safe switch, okay? It prevents excessive amount of current to flow. For example, let's say in a normal scenario, right? I plug this in, and then you see like this here, it says it has a rating, by the way, it has 3 amperes. 3 amperes means to say, right, this thing only allows 3 amperes to flow through. If let's say in an unlikely event, thunder strikes, sometimes thunder strikes to strike your house, then the whole house trips, right? This fuse is going to be your protection point. Okay, so when it detects excessive amount of current flows through here, inside this fuse, there's actually a wire. Yeah, there's actually a wire here, a specially engineered wire that allow only a certain amount of current to flow. So let's say, for example, if more than 3 amperes of current flow through here, right, the wire will literally fuse and break into 2. When it breaks into 2, it prevents current from flowing in there, because Because what happens is, right, the flow of current out will usually be like this. The current will flow in here through the live wire into your electrical device and then flow back out through the neutral wire. Okay, so it always has to go through the fuse first. Okay, this is very commonly seen in a lot of household electrical appliances. If you ever had any electrical device that spoils after a thunderstrike, right, which is most commonly your modem. Have you guys ever had a modem problem after lightning strike? Right.
What's the modem?
The one that's connected to the internet, bro.
Because it is Wi-Fi receiver.
No. Really?
So
Catch up, I'm gonna beat you later. But anyways, the modem is the one that connects the internet from your home, that connects the internet, and then the modem will be connected to a router that sends the Wi-Fi signal. Alright.
Yeah.
Got
So this wire connected that.
modem.
Connect from the big AC Wi-Fi.
Yeah. And the modem, the house, there will be an internet line that connects to the modem. The modem will connect to the router that sends Wi-Fi signals to the house. Okay, anyways, just think about the Wi-Fi device, right? Usually when thunder strikes, the most common thing that spoils at home is going to be your modem. Okay, then after that, most of the time, if you bring the modem to the electrician, right, they'll say that, hey, your motherboard spoiled already. I need to order and buy another one, and it will cost you maybe like $500. Okay, so actually, what the first thing they do is, right, because they're obviously electricians, right? They know what to check first on. They usually check for this thing. You know what they do? They literally open up this 3-pin plug. No, they don't break it. There's just this screwdriver here, right? Open this up, take this fuse out, put the new one in, and then connect it and see if it works. Most of the time it will work. Most of the time, because like I said, this fuse is used to protect the electrical device. Okay, so once they repair it, right, this thing is like $3 only. Then I tell you, oh, I need to order the motherboard and I need to replace it. That'll be $500. Then it's young money for them.
You just say, nah, never mind, we get back and then we'll buy it.
No, they won't let you do that obviously, because they'll have that way So my advice to everyone is, if you ever find your electrical devices spoil, right, literally open up the 3-pin plug, replace it, and then put it back in. Usually it will work. That's what happened to me with my printer also at home. After one day thunderstrike, it was heavy thunderstrike. I tried to print shit at home, right? Hey, my printer is not working. I'm thinking, oh my god, did they fry the motherboard? I panicked for a while, right? I'm thinking, like, oh, wait a minute. I teach this to my students all the time. I wonder if it really works in theory. I open up the 3-pin plug, replace another fuse. Obviously, I didn't have an extra fuse lying around, so I had to like open up another 3-pin plug, right? And take this fuse out and put it to my printer, and then turn it on. Oh, it works.
Oh,
It works.
is it BioBoy? Is it cheap?
You can find anywhere in a DIY or a hardware shop or literally the corner shop there down the road here. You can buy there. This thing is cheap, but it's not more than $5 probably.
My question is, right, so with an electrical socket, it's like a infinite amount of data can be sent from an item, right?
You mean this one?
Like awesome good.
No, this one here provides only maximum 240 only. But all our electrical devices use less than 20. But why you realize that difference? There's also something known as a transformer, which you'll learn later. That converts this 240 volts into, let's say, for example, 15 volts here. So
my question would be what's stopping like all 240 volts to just directly.
the transformer will stop it. Because the transformer will only output the designated. Yeah, you could say it's like a regulator. It regulates the voltage outward. Yeah, but there'll be a topic to learn about that later on. No, it's not your wall socket. Usually a transformer is like the brick, like the most common transformer that you see is the not Optimus Prime, the damn black color brick on your computer charger, you know, like laptop that brick, right? That thing is a transformer. Yeah, then you see coils and
Why would we break it? No, I didn't break it. I was just like,
Yeah.
found the data center. But
he was going through a phase.
I was like, because my computer part is part individual part.
Right.
I was retarded.
I did that once before, so with my first gaming laptop, I dismantled the whole thing. Yeah. Wow, the whole thing cracked. But anyways, that's the story for another day. Okay, so anyways, back to here, guys. So anything happens, you just need to replace the fuse and it's A-OK already. Okay, anyways, from this part here, you need to know a few things. The earth wire, the neutral wire, and the live wire. Remember, current flows in the live wire and comes out from the neutral wire, guys. And the fuse will always be connected before the live wire because it protects the electrical device, right? So yeah, everything else is nonsense. You don't need to know that much. Okay.
So what about the 2-pin plug? Does that mean they don't need to?
Okay, very good. That's a very good question. Guys, what about the 2-pin plugs? Usually you notice, right? Any electrical device that has 2-pin plugs, they generally use very, very low amounts of voltage only or current. Right? For example. Yeah. So it's like it's not even drawing that much voltage to have excess amounts of charges. So anything that's 2-pin plug, usually they require very little voltage only. Anything that's slightly higher will have 3 pins on. No. I think not. Let's ask Google.
What? What's your ask? Yes. Oh, I understood the 2-pin plug. Yeah.
Yeah, I don't think they have it.
Wait, then. Wait, what's the wire for here?
Discharge excessive amount of current. Sorry.
Oh.
Yeah, they don't have it. It's just wire only.
Yes.
Live wire and neutral wire only. So one current goes in, one current goes out. So yeah, no fuse.
Yeah.
But actually, why don't they connect it with fuse?
And also, why do all countries have like different standards of blood? Yeah, you see these like the British ones with options.
I think I googled that question before. It was because of the way they deliver the voltage or something.
But is it for the same everything?
That would definitely be better for everyone, right? But I think certain parts of the world don't, like for example here, right, is for sure 230 volts, right? But in somewhere else, maybe in Thailand, or sorry, not Thailand, but Taiwan, maybe it's only 210 volts only.
They can't afford it.
So you know what happened when I went to Taiwan, right? And I charged my phone, my whole phone spoiled, because I will use my charger from Malaysia, which has a different rated input, plug into their input. And then my phone like spoiled, like it was so weird. The signal and everything just stopped coming in. I think it fried some part of the motherboard. But everything else still works fine. Just that zero signal already. Zero.
I don't think that's making it good if you're rolling. Wait,
no, I tried everything, all the setting, everything. Just one day when I fell asleep and I charged it overnight, it just GG'd out already. It was I remember it was a Samsung Note 4.
Oh, so wait, doesn't that thing only specify battery we have stolen? How does it fuck up the phone?
No, because it's different input from here. So our charger, right, it is made to take in 230 volts. But if you bring it to somewhere else, right, maybe the voltage is different. Maybe it's 210 volts. Let me check. Yeah, you see, it's totally different. It's 110 only. Ours is 230, So it's like Wow, then it really stopped mine good, man. I was so sad. Anyways, back to this here. Right, so basically a fuse is used to protect the circuit, right? When huge current flows through it, it disconnects by fusing. The wire literally just burns out and then it breaks up. The wire literally breaks up, right? The fuse should be rated slightly above normal working. So let's say, for example, if this laptop is using 5 amperes of current, the fuse for this laptop, the plug thing, right, will be like maybe 7 amperes. It'll be slightly higher because they have to take into consideration the fluctuation of current, right, which could fluctuate high or low, you know. So it should be rated slightly higher, huh?
Is it other Chinese parents do this? It's like, oh, you plug in your phone overnight, it's going to explode in your face. So they
Yeah. It's true. For the older phones, but now no more already. For example, right? I don't know about your phone, but to my understanding, the new phones, right? They have something to regulate the current inflow one. So let's say, for example, right? I noticed this. If I plug my phone in at 12 o'clock, right? Or maybe 11 o'clock, right? My phone will detect that I sleep at the time, right? And it will limit the amount of current that flows in. So it will be like super slow charging. So it will like slowly charge until maybe like 5 AM, only it goes to 100%. But if I plug my phone in the afternoon, right? Maybe 1 hour it will full charge already. Because most of the phones right now has fast charging already, right? More current flows in. But at night, if you plug in, they will say, oh, sleep mode detected, and they will be slow charging all the way. So there's no such thing as overcharging. And the olden days, yes, the olden days actually you're not supposed to overcharge it overnight, because theoretically, yes,
What?
oh, then that's not good. Yeah, you can't like plug it in for 2 days straight, then obviously the regulators have a limit, right? Because why would you have your phone there for 2 days? Right. So, yeah. Fine. It's fine. The new phones are.
New one. How new but they have to
At least I would say 2020.
Oh, okay. Oh,
At least 2020.
fine. Quite the phone.
Yeah, so that's that. Okay, anyways, fuse and circuit breakers, they work exactly the same way. Okay. If anyone here don't know what a circuit breaker is? Circuit breaker? Anyone? Circuit breaker is literally that thing at the back there. You know that thing at the back there? Yeah, you know, sometimes when thunder strikes, right? Then the whole house blacks out, then your parents will go downstairs, flip open the switch and everything will work again, right? This thing is that.
Did you do?
Yeah, exactly. So this guy, okay. See, different these different buttons for different phases of this place. Okay. So on the thing. Yeah, it's very so you really need to put more fun later. Yeah, it's fun. Oh, something yeah, so something something someone's coming. Oh,
That's one.
so the whole thing would be connected to different things. Like
On the street, the station was rather nice.
yeah, and this means the chart. On the calculator. Yeah, because that's not the topic. Yeah, all of you wrong. Right? Now, instead of one, right, string or illustrate letters. And down here is print. Okay, if that's excessive on flows, the frame will still, and everything, so what you need to do is just that on the.
So if you were to turn off like a lot of these, then you walk around like wait, listen, everything being split equally throughout everything, like you know, so walk around flow of everything else. I mean, yes. So when you off everything except for like see right, that'd be like a solid we start from Fantastic Four like
No, that's right. But technically, but usually, especially these largely electrical appliances they'll have somewhat of a regulator, so that they don't allow too much current to go with it. Anyway, that's going to be a working principle, no way like suddenly everything off and anything you search for current, like.
so I want to let's say I went to a really high voltage factory where they take out a lot of energy, right? I turn every single thing on except for like one single branch of switch, right? In we put the power and things below us, and it I think power was before, right?
It looks that way, by the way, because there's gonna be some limitations, there won't be something like a surge of current flowing here. It's, I don't know how they construct the wiring, but they will have limitation one. I wouldn't have like, I wouldn't, like this thing here, right, I wouldn't let 100 ampere of current flow into it, but it's not designed to even allow that to go in, so
So
like everything else will not have all the current directed here. Anyways, guys, another interesting thing that I did with the knowledge of circuit breakers was, I know that it connects to different phases of the building, like when I was in college.
Literally turn off every single
Exactly. When I was in college, right, what I did the fun it's all without rare. I coordinated a mass fuse switch off because what I noticed was back then in Atamas, back then in Taylor's, you know, Taylor's was the Atamas, right? You know? There's this building, when they closed the chartered international or something. When in the Plaza lah, which is right next to Plaza Lama something lah. So what I did was right, I noticed that these were literally at the stairway from every level at a few places. I'm thinking like, oh, what would happen if I switch them all off together? Actually together because in one mean empathy or very. So what we did was right, I coordinated the passive off, right? I had like maybe 6 of us at 6 different locations, right? I said, okay, give me your walk, pick up your phone and start the timer as soon as I say. So I gave like maybe a 10-minute timer, right? Okay, everyone click it together. So everyone's timer started running down together, right? I say, as soon as the timer stops, start going to, no, as soon as we quit this thing, start going to your designated spots. I already coordinated everyone to be located at different places, right? As soon as the timer stops, right, reach 0, I want you all to flip off the switch together.
Was Gilbert involved in any of these?
Oh, okay. Yeah. Then like, okay, then after everyone stood in their position, right? I obviously picked the role, coincidentally, right? And some of my friends, they went to the high level. They told me, right, as soon as everything switched off, I literally it was like almost poked out onto the floor, I think. So it's like when we off everything up, the whole school back up again. The whole school back up, right? And then as soon as we did it, we started running back to our classrooms, right? And you can see all the guards and all the students started walking out, right? And we hear from the chatter of other people, right? With Taylor's no money, they fucking didn't pay for electricity on the last day. Then we're like, okay, let's go for a movie. And we go, no.
Last day again, you just anything one day, go after you so last day you need to laughing follow track. Do you go wait where did you go?
For college to leave. Then I went to the uni. Or uni. With the power way up, you can do a lot of things, okay, to make sure you don't be smart. Yeah, you get caught in your And once again, I want to mention that well, but this time it's only the ABC. Everything from the back. My yellow particular. But I this time
Very fine. Oh. So she was an interview and some of the stuff but we got it and I'm gonna go class like share of it. Shit, was that the now I'm sorry. You had them back in the front with the. No, there's no. Yeah, it's very covered. But they good. I mean, it's good. Okay. Oh, I see. Oh, that's very good. Shall we go on to this? Oh, play super. The other has no control. Yeah, we will. I'm here. You know, not see, I'm doing percent. I'm doing stuff. Yeah, so there's anything. It's like. So like. I'm really. And if our face is. Right? You should consider. I think good. No. It's okay. Things are all over. Thank you. This is the battery lighting part, but. I know it's in both like typically getting messages to be some. Oh, like in something about that. And then keep it. And then something. Something where it's
That's dangerous and dangerous. I don't know, batteries not completely then. That's gonna be a danger for sure. But I think the batteries, right, they did do something now, like the employees. Yeah, it's like. All the moment they can't imagine. So that was sitting in the lab, man. We saw the we saw the tire stand, we saw the button, but then I mean, burn the battery. What? We wanted it explode, but it didn't. It didn't. But maybe they didn't do it right on. But maybe we should do you touch the I don't clear. Don't look like it's something. Yeah. You get shot. Oh. I don't know why, plus you were young enough. Yeah, it could have been much worse. It could have been much worse. So we can say the type is not probably reasons it's the one
Chinese would so in terms of well, it's always big irritated. So I want to listening big to the point. So when big,
So the blue one after you have water and different, we didn't go in after the fish. It adds the this and okay, wash it and then. Okay, but they get. Okay, we don't. It's not very. Interesting. That's all for today. Just going to be the NBC almost. Right.
hopefully like everything after the news.
Yeah, until you see the 1.5, that's it really.
Then next week, we come back, we're gonna do some vision.
In Google and something, hey, this is so complicated. Bro, you don't like it, you just.
I don't do it per se, you know, all activities.
Guys.
I know the viewing connected.
Oh, bye, Charles, that's it for today.
What's the homework, sir?
What?
Because of work.
What's the
Homework is not an ABC, bro.
Huh?